Ooh, y'all stuck around. I'm impressed. Oh. All right. So my talk is building on the shoulders of giants, and if I turn my head, you can't hear me as well. That's not going to be good. All right. I feel like Batman. I can't turn my head. I'll make it work. All right. Except it's not working. All right, let's try it. You know how Mac keyboards don't work? I think mine just died, so I'm just going to use the mouse. This is going to be bad. All right. In the late 1950s, people were becoming uneasy how each new computer spawned its own language. At the time, programming languages were provided by the hardware manufacturer. Each new hardware came with a new language. They deferred every model was a new language. The first language to be consistent across models was Fortran, but even that was only consistent across IBM computers. A committee was formed to design the first truly universal machine-independent programming language. The keyboard worked again. All right, we'll do better. In January 1960, 13 computer scientists met in Paris for an unprecedented meeting with the goal of developing such a language. There were 6 delegates sent from America and 7 delegates from Europe. One of the delegates, Alan Perlis, said, "The meetings were exhausting, interminable, and exhilarating. One became aggravated when one's good ideas were discarded along with the bad ones of others. Nevertheless, diligence persisted during the entire period. The chemistry of the 13 was excellent. And the result of this meeting was the language ALGOL." Cheers for ALGOL. I heard someone. All right. About this language, Tony Hoare wrote, "Here is a language so far ahead of its time that it was not only an improvement on its predecessors, but on nearly all of its successors." In spite of that, Tony created a successor to ALGOL, along with Nicholas Wirth. He actually made the statement after he created the successors, which I don't know if that means. But so with Nicholas Wirth, they created ALGOL-W, which in turn led Wirth to go on and create Pascal, which was initially published in 1970. Independently, CPL was created at the University of Cambridge as the Cambridge programming language. It led to BCPL, or Basic CPL, which is a much simpler version of CPL. Then at Bell Labs in the United States, Ken Thompson and Dennis Ritchie went on to create C, mainly based on BCPL, and shortly after its successor, C. And so we have in the US a language development tree and a separate one in Europe. In Europe, Pascal flourished, and it spawned many successors, including Oberon and Modula. In the US, C proliferated, and it enabled many languages, including C++, C#, Java, and JavaScript, Python, and many, many more. By 2007, dozens of languages existed that can all trace their roots back to a common ancestor, ALGOL. Which begs the question, why another language? And to understand that, we have to look at the environment for which Go was born. So 10 years into Google, Urs, the head of infrastructure, said, "At scale, everything breaks, no matter what you try and do, and you have to deal with that reasonably cleanly." You have to deal reasonably cleanly with that and try to hide it from the people actually using your system. Next, tell me when you're going to take the pictures, because I All right. Yeah, or just the slides, that's fine too. Yeah, I photoshopped the pictures on those, so I'm just kidding. All right. In the first 10 years, Google had experienced scale unlike the world had ever seen before. This chart shows how many multiples we grew, from hundreds to tens of thousands of times. In addition to machine scale, Google headcount also grew significantly, from well under 1,000 employees to over 24,000 by 2010. And Urs said keeping things simple and yet scalable is actually the biggest challenge. The biggest challenge that Google had was keeping things simple and yet scalable. And yet Google struggled with that challenge, especially with its engineering efforts internally. So Google's scale brought massive complexity. We had huge code bases with many, many dozens of programmers working on them at the same time. We had very large build farms. And in spite of parallelized builds across massive build farms, we still had over 45-minute builds. And so Brian Kernighan in 1976 wrote, "Controlling complexity is the essence of computer programming." And so when faced with complexity, what does a good computer scientist do? And during one of those 45-minute builds, Rob Pike, one of the creators of Go, decided during one of those builds there was a meeting being held by two individuals who were speaking on, they were members of the C++ committee who was designing C++ 11. And so they had a meeting where they talked through the different features, and Rob and his office mates went to this meeting, and they took about an hour and they outlined 35 different features that they were trying to include in C++ 11. And at which point Rob asked himself a question. Did the C++ committee really believe that what was wrong with C++ was that it didn't have enough features? Surely it would have been a greater achievement to simplify the language rather than to add to it. Rob returned to his desk with his office mates, and this really got them thinking about what should a modern practical programming language look like. And so they started another 45-minute build. And during that time, they started writing on the whiteboard. And by the time the build was done, they had already sketched out the beginning of a language. His office mates were not your average office mates. One of them was Ken Thompson, who I'm sure you're familiar with. He's from the US. He is the author of B and C and Unix and UTF-8 and a lot of other things that we've used today. The other office mate was Robert Griesmer. He comes from Europe. He studied under Nicholas Wirth. And he was responsible for the Java Hotspot JVM as well as the V8 virtual machine. And so Go is, so we've got Robert from the European branch and we've got Ken from the US branch, and Go is the first language that can claim heritage of both this European and US branch of language design. In a very real sense, it has unified these two branches, as well as a third branch that we'll talk about later. In speaking of Go's inspiration, Rob Pike states, "We built from scratch, borrowing from C only minor things, like operators and brace brackets, and a few common keywords. And of course, we borrowed ideas from other languages we knew." Now, this is a list of some of Go's many ancestors and influences. I'd make the claim that there's never been a set of language designers with broader or deeper language design experience than these three. They had a rich knowledge of what came before, and they knew just what to cherry pick. Now I'd like to share with you 4 design principles that guided the development of the Go language. Principle 1, evolution, not revolution. The idea is that most ideas aren't new at all. And a really important way another way to rephrase this is that new languages should consolidate, not invent features. And Go held true to that. There's almost not in fact, it's a common criticism of Go, is that there's nothing new in it, which is mostly true. And that's what we designed on purpose. That was one of our principles guiding it from the beginning. The second principle is waiting for good design. There's many instances of this throughout Go's history. The general idea is that when you're designing a language, there is no undo. If you say no today, you could always say no, yes tomorrow. If you say yes today, you're stuck forever, or at least for a really long time. The author of Effective Java, Josh Block, says, "When in doubt, leave it out." Principle 3 is consensus-driven design. And part of our goal was to make it as simple as possible, but no simpler. Ken Thompson brought this practice in from Bell Labs. He writes, when the three of us got started, it was pure research. We started off with the idea that all three of us had to be talked into every feature in the language. So there was no extraneous garbage put into the language for any reason. And Tony Hoare writes, there are two ways of constructing software design. One way is to make it so simple that there are obviously no deficiencies. The other way is to make it so complicated that there are no obvious deficiencies. By design, Go's approach is minimalistic. With the goal of simplicity, we tried to create a language with as small feature set as we could, while keeping it productive and useful. A lot of features common in other languages were left out of Go, including header files, classes, inheritance, constructors, pointer arithmetic, uninitialized values, annotations, templates, exceptions, globals, void, and the list goes on and on. In fact, I was just talking with Heather. She was asking questions about Go, and I forgot that some of the features that we don't have in this language led us to not have problems that are in common in other languages, which is that we only have static builds. There's no dynamic loading. All right, so there's a lot of features left out of Go. The last principle is that of rapid iteration. When you're in the design phase of a language, you need to make frequent and sometimes dramatic changes. You need to go forward with that expectation and build your design process around it. So within a few months of that 45-minute whiteboard session, the team had grown to 5 with the inclusion of Russ Cox and Ian Lance Taylor. At this point, this was a few months into the project, all the Go source code that existed was in a single repo. And whenever they made a change, they would need to fix it in the 1,000 or so files that existed all at once and then commit it back to the repo. And they did this pretty regularly. The mechanism they used worked quite well, although we knew it wouldn't scale very long. What would happen is Russ would sit at his desk and he'd open up every Go file in existence in his editor, and then he'd do a series of regex search and replaces. Well, Rob, Robert, and Ken stood behind him, looking over his shoulder, and they would nod, and then he'd commit. So they spent many months doing this, the process of discussion, planning, prototyping, experimenting, and whiteboarding. A key part is they added one feature at a time. And so it was very methodical and slow the way they added a feature. Consensus continued to drive the process. They also built 2 distinct and separate implementations, which ensured that the spec was accurate. So we spent 5 years developing Go. It was born as a 20% project at Google in 2007. About 2 years later, it was open sourced in 2009. And by 2012, we released 1.0. And we told people we're not going to make changes to the language. At this point, we were shifting our attention from designing Go to using Go. And so what is Go? But by show of hands, how many people have written Go code before? Whoa! I was not expecting the number to be that high. All right, I'm not going to ask any more questions. That was a lot. So we asked a group of people on a survey. We asked thousands of people what they thought of Go. And these are the most common answers they gave. Go is concurrent. Go is simple. Go is powerful. It's fast. It's expressive. It's readable. It's type safe. It's compiled, but compiled very, very quickly, which gives it a dynamic feeling. Go was well received, especially by the open source community, who first embraced Go with notable projects, including Docker, Kubernetes, and Hugo. And since our 1.0 release, Go has had steady adoption. Earlier this year, JetBrains awarded Go the title of the most promising programming language. It discovered that, from its survey, it found 12% of developers today are using Go. And 16% of those surveyed said they were intending to use Go in the next year. Other surveys show slightly lower numbers, so I don't want to overstate it. But what? 16% are intending to use Go in the next year. So 12 plus 16 is...
Of the 12% using it now, they're not expecting to use it in the next year.
I should restate it. There's an additional 16% who are intending to use it in the next year, which, what is 28? Is that right? 28? We're not there yet. We're only at the 12. We'll stay with the 12. Our total of worldwide users, we estimate, is between 1.5 and 2 million. And we believe this to be an accurate and actually relatively conservative perspective of it. We've got Gophers spanning the world. Does anyone know where this is? Iceland. That's good. So we had a conference there last month, and we actually had Gophers spanning the gap between the two different tectonic plates between the continents. It was a pretty great idea. My wife took this picture, so. All right. I'd now like to turn our attention to 3 specific features of Go, which I think you'll find interesting for us to explore a little deeper. The first is Go's approach to object-oriented programming. This might not be a popular opinion. It might be a popular opinion in this room, but it's probably not a popular opinion outside of it. But it is our experience that when you write programs as inheritance-heavy subclass systems, it forces you to make design decisions very early that are very hard to change later. And so we knew we didn't want that. Dan Ingalls, who's the implementer of Smalltalk, said, if any part of a system depends on the internals of another part, then complexity increases as the square of the size of the system. This should look familiar to many of you. It's, this is a Java one, but it could be in any modern object-oriented language. There's dependency graphs all over the place. The relationships are everywhere. This isn't even a particularly complicated one. And we see this exponential complexity coming from inheritance. Rich Hickey, the author of Clojure, said, it's my opinion that object-oriented programming, as delivered by Java, etc., is not a good default way to structure your program. But object orientation existed long before Java and C++. Before them, there was Simula. Simula took Algol and added to it objects, classes, inheritance, and subclasses. It's considered the first object-oriented programming language and was influential in the development of Smalltalk and all following OO languages. Dan Ingalls, the implementer of Smalltalk, said, Simula changed from the procedural view. They flipped it around, the object to the object-oriented one, which is that within every type of object, you have all the procedures that work on it. So next came Smalltalk, where everything is an object, and objects are only communicated with via the sending of messages. Alan Kay, the creator of Smalltalk, said, I did make up this term, object-oriented, and it was a bad choice because it underemphasized the more important idea of message sending. Smalltalk object orientation is about message sending, which is an oversimplification, but it's not an inaccurate one. And Go's object orientation is patterned after Smalltalk's. There's only 2 mechanisms in Go that provide our object-oriented functionality. The first one is methods. It took us a while in our design to realize that the right way to do this was focus on methods and not data, and permit methods on any type. And I'll walk through an example here. So we're creating a new type. This type is in Go, this is a slice of ints. Slice is our word for a dynamic sized array. And then on the second line, we're creating a method. We're binding it to that type. We give it a name and a return value. The second component is interfaces. Interfaces are the mechanism to support an object-oriented programming style. They give you a form of dynamic dispatch. And so now we'll create an interface. So we've defined a new type here. We give it a name. The name is stringer. That's a Go convention that it becomes an of whatever you're doing. And then we declare it as an interface. And then we define all of the methods that are part of that interface. In this case, it's just a string. So if it has a string method, it satisfies the stringer interface. And next, we'll define a function. This function accepts a stringer. And then we're just going to print it out. But what we're going to print out is the call to that string method. In Go, interfaces are implicit. They're not explicit. So if you remember earlier, we actually defined the method that satisfied this interface. We defined it before we even wrote the interface. In Go, they're as independent from each other as possible. And so to tie it all together in our main function, we will, most of you know Go, so this is actually not that bad. We define a new value, and we declare and set it to a phone, which we give an initial value of this string, well, the set of integers, and then we call that print method. And because the phone, the P, has the method string, it'll work there. Dan Ingalls writes that when you try and break a complex problem down, you want to try and break it down into as few parts as you can. And you want them to be as independent as they can be. Go's approach to interfaces and methods are as independent as possible. Any type can satisfy any interface as long as it has the right methods. Any interface can be defined before or after the types that satisfy it. It just works, and it works really well. And so Go's OO story is pretty simple. Methods provide message sending mechanism on any type, and interfaces provide reusability through dynamic dispatch polymorphism. So Go is object-oriented in a very real sense, as defined by Smalltalk, even though it doesn't include classes, objects, or inheritance. Too far. The second topic I want to talk about is concurrency. So before we get into that, I want to talk a little bit about definitions, and maybe you've heard this before, but Rob Pike says concurrency is not parallelism. Concurrency is about dealing with lots of things at once. Parallelism is about doing lots of things at once. Parallelism means running code on multiple CPUs at the same time. Concurrency is about writing programs in a clear way so that it's easy to explain how the program does many things at once. If you only have one processor, you can still write a concurrent program, which will make it easy to understand, but it can't run in parallel. But if you do have multiple processors, there's an obvious way to parallelize a concurrent program. Joe Armstrong, the creator of Erlang, says, the world is parallel. We want to write programs that behave as other objects in the real world, then these programs will have a concurrent structure. So although we shifted topics away from object orientation to concurrency, I think Joe's making a case here that a truly object-oriented language must be concurrent. So our Go's concurrency story begins with Douglas McElroy, who back in 1964 came up with the idea that became Unix pipes. And he did so with this memo that he sent at Bell Labs. The relevant part is the first one, which is, he says, we should have some ways of coupling programs like garden hoses, screw in another segment when it becomes necessary to massage data in another way. This is the way of I/O also. And since I'm actually a little ahead of time, I'll tell you an interesting story about how Unix pipes were created. He had this idea in 1964, and he spent a lot of time thinking about it. From the period of 1970 to 1972, he was pestering Ken and Dennis and the team at Bell Labs, and he kept saying, how about we do something like this? And he'd give them a proposal and another proposal. And then one day he came in with the syntax. He finally had the idea of the right syntax for shells that went along with piping. And he gave it to Ken, and Ken said, I'll do it. He was tired of hearing all these proposals over and over, and so he said, I'm going to do it. And he didn't do exactly what Doug proposed. But he went home and he invented a slightly better approach, and that approach got changed once more to the one that you're all familiar with. But Ken did it one night. He just decided that night he was going to go home, and he implemented Unix pipes all in one night. So by 1978, so fast forward a little bit, there were many proposed methods in use for communicating and synchronizing in the context of programming multiprocessors. Shared memory was the most common communication mechanism. During this year, Tony Hoare published a paper which changed everything. It was decades ahead of its time, and he called his paper Communicating Sequential Processes, or as it's better known today, CSP. Just to break down those words a little bit, in his definition, processes is a unit of execution. Sequential meant that each of these ran as an ordinary single-threaded program, and they communicated. And the way they communicated was over unbuffered channels, and that provided a form of synchronization. In his paper, yeah, that would help. Thank you. In his paper, there was no sharing of memory, there was no threads, and no mutexes. And they made an improvement over Unix pipes in that they could be connected in arbitrary patterns. Hoare also got the idea to include the prime sieve, and Doug McElroy actually gave him this idea. In mathematics, we also call this the sieve of Eratosthenes, which I might not be pronouncing right. There's a lot of words I might not be pronouncing right, but I'm going to do my best. Are we familiar with this? No. Good. I was hoping some people wouldn't be. I wasn't, I'll be honest. So what it is it's a simple algorithm that was created in ancient Greece around 200 BC for generating prime numbers. And Douglas McElroy came up with the concurrent version of this, which is the one I'm going to show you next. So the algorithm is pretty straightforward. You have a process that enumerates all numbers from 2 incrementing whole numbers up from there. Then there's another process that takes those numbers, and it starts with the lowest number is going to be the prime number, and then it filters out or it eliminates every multiple of that number. And then that goes to an output to another process that repeats. And this one takes the lowest number and filters out all of the multiples from that number. And it keeps going on and on until all you have left is prime numbers. The animation's slower than my explanation. And yeah, I did that. I animated that. All right, so in this paper, he included the prime sieve, and this is in CSP. We're not going to dive into it because, frankly, it's hard to break apart. But an interesting thing is in the bottom here, we've got these different processes communicating to each other through the pipes, and he used similar notation to Unix pipes. CSP has inspired 3 different branches, which all emerged from this paper. The first was Occam, which was created in 1983 and is the closest representation to the paper. In fact, Hoare advised them in their implementation. The next one was Erlang, which was created in the late 80s and focused on the functional side of CSP and used mailboxes to communicate between processes. Go's story begins with Rob Pike, but not this Rob Pike, this Rob Pike, a much, much, much younger, more naive one, back in 1989. And he was working at Bell Labs, and he worked on a successor to an even earlier language called Squeak. And so this language is called NewSqueak. And NewSqueak was a research language. Its goal was to make concurrency that was in Squeak, which was a toy language, practical. Syntactically, it was pretty similar to C, but like CSP, it used channels as rendezvous points for processes. And I'll show you the prime sieve in NewSqueak, which we also won't talk through, but I'll talk about a couple points on the second side here, which is a big change that he made was that channels became a first-class citizen. Unlike its predecessors in CSP and Squeak, channels you could store as values, you could pass them along as parameters, you could even have channels of channels. You also introduced a couple syntax points that will become important when we get to Go, which is the channel receive, which is the arrow sign pointing left, as well as the colon equals. Next in this branch is Aleph and Limbo. Anyone here an Aleph Limbo programmer? Seriously? What? It had to have been, yeah. So these were both languages that Rob and others used inside Bell Labs for writing real system software. Unlike the research language and the toy language of Squeak and NewSqueak, these ones were functional and you could write real code with them and ship code with them. Aleph was written for Plan 9, which was Bell Labs' successor to Unix, and Limbo was done for Inferno, which was Bell Labs' successor to Plan 9. And so both of them real system software. They both built on the concurrency ideas of NewSqueak. Aleph wasn't garbage collected, and it was really painful. In fact, in all of the Aleph code, about 50% of it was spent to managing memory. Limbo was garbage collected, and it was a really efficient garbage collector. And it was so good that it convinced Rob and the other people at Bell Labs that you could write a performance systems language that was garbage collected. It also, using these languages, convinced them that CSP was a great mechanism to write concurrent programs like network servers. And that takes us to Go. So for Go, we have two mechanisms that provide concurrency: Go routines and channels. And we'll talk about each of them. The first one is Go routine. And a Go routine is pretty simple. What you do is you put Go in front of a function call. And what it does is it makes that function execute independently. Each of these Go routines have their own stack, which grows and shrinks as required. And they're very, very cheap. In fact, it's common to have thousands or even hundreds of thousands of Go routines in your program. It's not a thread. The Go runtime will multiplex Go routines onto threads as needed. But in fact, it's not uncommon that many, many Go routines will run on a single thread. So Ryan Dahl, the creator of Node.js, said, "I like the programming model of Go. Using Go routines is so easy and fun. If you're building a server, I can't imagine using anything other than Go." And reality is, it is fun. Who thinks maybe you guys do, but concurrent programming is usually not thought of as fun. It's usually thought of as painful, but Go really does make it fun, like Node was. But anyway. The next is channels, which are going to look quite similar to the last few languages which we discussed. In fact, Go changes very little from the languages that we had. You can declare and initialize a channel. You can send a value onto a channel. You can receive a value from a channel. They both use the same arrow. And the important thing to remember is that data flows the way the arrow points. So if you want to put it onto the channel, the flows make sure the arrow points into the channel. If you're receiving it from a channel, make sure the arrow points away from the channel. So now I'd like to walk through the prime sieve as written in Go. And I'll start by saying I think this is one of the most elegant pieces of software I've ever seen. As I studied it more and more, I didn't write it, but as I studied it, I just continued to be impressed by the implementation. So we'll walk through it, the whole thing. First, we create a function called generate. And this function has one parameter, which is a channel. And this is a specific type of channel. It says all we can do is this channel can only receive. And it's a channel of integers. Then we have a for loop, which you know how for loops work. And what we're doing is we're sending the value inside this for loop onto the channel. Our second function is filter. And this filter takes three parameters. The first one is a sending channel. The second, a receiving channel. The second one is a sending channel. And the last one is just the integer, the prime. And so what this is going to do is it's going to take that input and it's going to filter it out. And so first what we do is we range over the channel. All right, this is like a for each for all the values in the channel as they come into the channel. Then we do pretty simple. We divide it. If it divides cleanly, then we know to filter it out. And if it doesn't divide cleanly, then we put it onto the destination channel. And that's that entire function. Now, the last function ties them all together. So this is the main function. We start by creating a new empty channel. Then we call generate in a Go routine. And so this is going to continue to generate. And we pass that channel into the generate function. Next, we're going to loop 100 times. And this will give us 100 primes. All right. Now we pull off the first number in that channel. By definition, that's got to be a prime. It's the lowest value of that channel. And we're going to print it out. And then we're going to make a second channel. And this is going to be the destination, the next part of the next process to run. And we're going to call filter in a Go routine. We're going to pass the source channel, our destination channel, and this prime number. And then we're going to set the destination as our new source for when we iterate again. So this line generates 100 primes, but we could also just have a simple for statement with no parts to it, and it will generate primes forever or until we Control C. Does that make sense to people? Was that easily read a code? I'm getting enough nods. All right. It took me a while to parse that, but it's really elegant. It helps to go line by line, I'll just say that. All right. The next feature I'd like to talk about is go thumped and go fix. So the first one's go thumped. That's how we pronounce it. If you say it the other way, it's okay. But we say go thumped. And what go thump does, it's pretty straightforward. It takes unformatted Go code and it formats it. That's what it does. Behind the scenes, what it's doing is pretty interesting. So we have a package that its sole purpose is parsing Go code into the syntax tree. We have another package which takes those syntax trees and prints them out as source code. And those are both in the standard library. And so what Go format does is it uses those two packages together to print formatted Go code. Probably the most impactful thing that happened was this ended all style debates in Go before they even happened. So an unforeseen and wonderful artifact of Go thumped is that there's no fingerprints on Go code. Looking through all the source code that our team has written, it's impossible to tell whose code is whose. It's also impossible to tell which code is generated versus which code is written by hand. And that's because it's all generated. In fact, there's no handwritten Go code. All code written in Go is machine generated. But it's done so in a way that looks and feels natural. This is not something you'd typically think of as a language feature. But it's something we planned from the very beginning. In fact, it was the last thing we did before we open sourced Go, which doesn't mean we waited to the end. It meant it was our blocker. We weren't going to open source Go until we had this as part of it. We didn't want Go code out there without this functionality in there. Not everybody was on board with it, but it turned out to be the best thing, one of the best things we did. And now a bunch of other languages are doing it, including C++ and Rust. Russ Cox, on a mailing list in 2009, wrote that once you have Go thumped, it becomes very easy to insert mechanical processing between parsing and printing. So we have all the hard parts of a program manipulation tool just sitting, waiting to be used, which takes us to Go fix. So I imagine a lot of hands went up. A lot of you have used Go thumped. How many of you used Go fix? Not a lot of hands. Good. That means I'm going to teach you something. So what is Go fix? Go fix is a tool that rewrites programs that use old APIs to use newer ones. It's much more intelligent. If you remember back, Russ was writing, had all this source code open on his editor, and he'd do all these commands, and that's how he'd iterate quickly. That idea never left him, and so when he had the opportunity, he wrote GoFix to be able to do it for him automatically. This is much more intelligent than regex writing. And it allows API changes to be shipped along with code changes. So I'll use an example. It's a pretty simple one, so we could fit it all on one slide. But originally, there was just one multi-hour OS open. This mirrored the Unix calls. And it's not a very nice API to expose to our users, and we wanted to improve it. As such, it's not something you could use with regular expressions either, because everything looks the same. You really needed to understand it. And GoFix let us take this bad API and replace it with something dramatically better. So to be able to do this, that tool needed a deep knowledge of the internal structure. With GoFix, it was really easy to do. Later, we used it to make more significant changes to our Reflect package. In fact, we refactored the whole thing. Russ wrote, the recent Reflect changes would have been unpalatable without automatic conversion, and the Reflect API badly needed to be redone. GoFix gives us the ability to fix mistakes or completely rethink package APIs without worrying about the cost of converting existing code. With this, we've barely scratched the surface. There's a lot of things we want to do. In fact, there's a lot of ways for your computer to help you write and maintain your programs. One thing I'm going to talk about in a little bit is Go dependency management. An idea that we're thinking a lot about is that if you issue a breaking change, the idea of shipping a fix alongside of that, so that not only can you upgrade to that, but GoFix will rewrite your source to be able to upgrade for you. And there's obviously going to be the right way to do that so that it doesn't rewrite all your source code for you and you can have input in it. But that's a pretty powerful thing if you think about it, that it can upgrade not only your packages for you, but also your code to be compatible with those packages. Another thing we can do is look for problematic patterns and apply a fix directly for them. Now I'd like to talk about the future of Go, or as we'd like to call it, Go 2. So the first 5 years of Go's life, we spent developing it, and then we shifted our attention to using it. And so for the next 5 years, we spent using it and refining Go's implementation. During that time, we rebuilt our whole compiler from C to Go. We took our garbage collection pause time down to under 1 millisecond. There were lots of improvements made internally to it, but the language itself remained pretty static because we wanted to focus on using it. In 2017, 5 years later, we announced the beginning of Go 2, which meant that we were shifting our attention from using Go to developing Go again. So what is Go 2? Go 2 is a series of releases. It's a process of language design. There might be a Go 2.0 release, but as it's currently stated, we have no intention of having a backwards breaking release. So we really think of Go 2 as really the process of rethinking language design again and being able to make more significant changes. Go started as a collaboration among 3 people. And Go continues to be designed with a collaborative approach. I can't tell you all the features in Go 2 because even as the product manager and responsible for the language, I don't know them because you haven't given them to us yet. Right? It's collective that we're going to do this together over a series of many releases. The way that happens is with the Go proposal process. It's very simple. You go to this URL, github.com/golink/proposal, and there's a template there. And you submit the template as a GitHub issue, and then discussion begins. And the discussion happens within our community, and lots of discussion happens. And eventually, most issues, the decision is made by the community. They come to consensus. And then those will be made, depending on the consensus, either go in or stay out of Go. There's also a review committee on the Go team that looks when there isn't consensus, helps to make some decisions. The point is it's open and it's easy to use. Please propose. Over half the proposals that go into Go come from outside the Go team. And the Go team follows the same process. I'd like to talk about dependency management. It's one of the features in fact, it's the first go-to feature that we're shipping. It's also one that our users have been asking for a long time. For our Go 1.0 release, we actually shipped with dependency management built in. We call it Go Get. And here's how you use it. It's pretty straightforward. So in Go code, an import statement looks like the top line here. This is one of my packages. So it uses a canonical address that resembles a URL pretty closely. And then on the command line, you'll type Go Get, and you can give it the package name that you're working with or the dependency, and it'll read all the source code import statements, and it'll get all the dependencies, and it'll continue to do that. So Go Get makes sure that all of the code you need is where it is. And it got a lot right. There's no configuration outside the source code. It's just import statements. It's very easy to use. The URL-like import paths eliminated a central hub. So you publish Go packages by putting them on any repository anywhere. You can host your own. It worked very well in practice, and it eliminated diamond dependency problems. But it also had some things wrong. The only update operation was upgrade everything to the latest code. There was no explicit concept of versions at all, which meant there was no good way of making a backwards breaking change. And it also resulted in unreproducible builds. And this might be one of the hardest points we had to deal with, is because everything always updates to latest, every time you build something, it could have different dependencies on a new computer. For Go 2, we're reimagining Go Get. There's a lot that goes into dependency management, easily enough to fill up an entire presentation. I'm just going to focus on one of the changes, which we call semantic import versioning. When we released Go 1.0, we issued a compatibility guarantee and encouraged our package developers to give similar expectations of compatibility. We later canonized this in what we now call the import compatibility rule, which is if an old package and a new package have the same import path, then the new package must be backwards compatible with the old package. By extension, this means if a new package is not backwards compatible, then it must have a different path. Since we released Go 1.0, the industry has standardized around semantic versioning, which gave us a great mechanism. In semantic versioning, as a refresher for many of you, the major version is the one to the left, and this increments when you create a backwards breaking change. The middle digit is incremented for new features, and the last digit is only incremented when there's bug fixes. Because the major digit, all the way on the left, is only incremented for backwards breaking changes, it gave us exactly the mechanism we needed to work well with our import compatibility rule. And so for semantic import versioning, we've inserted the major version into the import path. And here's how it works in practice. You notice it's not very different. You'll make an import statement. The import statement looks the same as before, except now it has v2 as part of it, or whatever version it is. It still uses a canonical address. We also took the opportunity to refine it. You can still Go Get, but we noticed that there was when you did a Go build and there wasn't a package already, it would tell you, you're missing this package, run Go Get to get this package. The command knew exactly what to do. It told you what to do, but it didn't do it for you. Instead, it gave you an error and a job to do. Computers are supposed to do our jobs, so we did that. We made computers do our jobs. So now when you run Go Build, it'll get all of your dependencies for you and build them. There's a lot of other big parts to this. We created a new thing called modules, which in Go is different from packages, and it's different from repos. It turns out to fit very well with how most people were already organizing their projects. So modules is more akin to a project. We created the minimum version selection, which you can read about on the Go blog. It's a new algorithm that makes defining your minimum dependencies very simple. It also provides reproducible, verifiable, and verified builds. And it's integrated into the standard Go tools. In fact, it's virtually the exact same workflow. Our users need to do almost nothing different to be able to get a lot more features. This will ship in Go 1.11. So Go.111 is the first of the Go 2.0, the Go 2 releases. And this will happen in August 2018. Also in this release, we're improving debugging and latency diagnosis. We have improved garbage collection automatic tuning, which is the only kind of tuning. And we have experimental support for WebAssembly, which you all heard about yesterday. I can't talk about the future of Go without talking about generics. And I don't know you're going to like the answer, but you're going to hear it anyway. So it might surprise you to hear that it was discussed from the very earliest of days. Ian Lance-Taylor, when he joined the team, was very interested in adding generics. In fact, over the last 10 years, he's floated around about one proposal per year to try and get generics in the language. Each of them have had pretty serious problems with them. Last year, we published all of the proposals so that everyone in the community could see all the ideas and work that's gone into it. In short, we're still thinking about it. And as a reminder, Josh Block told us, when in doubt, leave it out. We also had friends that worked on Java generics, and they gave us some really clear and uniform advice. Every one of them said the same thing: don't do it. They said, don't do it, and so we didn't. They said, wait as long as you can. Don't do it until you have the right implementation, you're sure you need it. And this goes back to our waiting for good design. We have nothing against generics. Many people would love to have them in the language. And as soon as we get the right design, we're happy to include them. We just need to get that right design. So what is the legacy of Go? Isaac Newton in the 1600s said, if I have seen further, it is by standing on the shoulders of giants, which is actually a rephrasing of a much earlier quote from John of Salisbury. This is so old that they didn't have last names yet. They just had cities where they were from. And so Bernard of, how would you pronounce that? But he's from English. We'd still say that? All right. Chartres. Bernard. Well, then I'll say it like that. Chartres. Bernard of Chartres. Close enough, maybe? Used to compare us to dwarfs perched on the shoulders of giants. He pointed out that we see more and further than our predecessors, not because we have keener vision or greater height, but because we are lifted up and borne aloft their gigantic stature. In a very real sense, Go was built on the shoulders of giants. I didn't draw the background one, but I did put them together. David McCullough writes, history is who we are and why we are the way we are. We are each shaped by the history of what came before. In Go, it's impossible to look at it without seeing reflections of many of its ancestors. We are hugely in debt to the many languages and individuals who laid the foundations for us to build upon. And we hope that Go has raised the shoulders a little bit more on the giants and might be a springboard for the next generation of computer scientists. Thank you. I won't be offended if there's no questions because it's the end. And it's like 7 o'clock and I'm sure people are hungry. But I'm happy to have one token one, so that's good. Thank you.
Hi, thanks. Can you give a hint how GoFix works? Is it a set of transformer writing rules or what is it roughly?
So GoFix, what you do is you set up a GoFix file, which is just Go source code, but it calls the right APIs to make the transformations needed. And then GoFix runs these Go programs, these Go scripts on a bunch of Go code. Does that help? Maybe.
So like you're saying how old API should be implemented using a new API or the vice versa?
So what GoFix does is it gives you the tools necessary so that you can very easily write a script that will convert callers of your API, your old API, to callers of your new API.
Okay.
Does that make sense?
Yeah, I think so. Yeah, thanks.
Okay, I guess I can.
Okay.
Microphone. Hey. First of all, thanks for this. It's been very informative. When talking about dependency management in Go2, you mentioned the idea of semantic import versioning. And I'm having a hard time seeing the difference between simply doing regular imports in Go1 that have the URLs that include the manager version in them from the new approach, which seems to only just call GoGet for you if you forget to do that.
Superficially, they look identical.
Yeah, exactly.
Right? On the slides I presented, there's no difference. Behind the scenes, the difference is the Go system is aware of versions. So they can come from the same. So today in Go, the way you would version before we release this is if you want to make a backwards breaking change, you actually have to create a new repository in a different location. Right? This allows you to keep your same repository with all of your history, but you can tag things as different releases and different versions, which is the big difference there.
And one small follow-up question. The fact that you specify a semantic version doesn't actually mean that my code is still compatible or non-compatible. Are you doing any verification of that? Are you planning on doing something to ensure?
We're talking about it. Yeah, reality is we have a lot of tools to be able to do some things. If you change semantics, but you don't change, signatures and stuff, we can't detect that. But that's no different from anyone else's code today, right? Anyone who uses semantic versioning has that same issue. So we can do some, but we can't do everything. But we think we can get pretty far with it.
Perfect. Thanks.
I just wonder, are there any plans for a preemptive scheduler for Go?
I don't believe so. But file a proposal.
Right.
Yeah, I haven't heard of it on the schedule.
But there hasn't been any discussion or anything about it, or?
Oh, I'm sure there's been a discussion about it. Just search on GitHub.
Okay.
And you'll find the previous proposals. But I don't know. It's not on our near-term radar. But again, a lot of things aren't. File a proposal, and that's how changes are made. I see hands, but no mic.
I got a mic.
You've got a mic?
Yeah.
All right.
I was just wondering, with the dependency management, you can depend on. Can you depend on a full version or just on the, let's say, only on the major version? Why can't you just depend on, let's say, 2.3.1, exactly that version?
So good question. What I didn't go into was, so in the import statement, it's only major versions, because a major version has to be backwards compatible. Right? That's the guarantee that you make when you increment a major version. There's also a mod file, which will specify the minimum allowed version, right, which can be more granular. Right? And this also follows semantic versioning. It's all you can do is do a minimum, right? And it's not uncommon. A package introduces a new feature. It's backwards compatible, right? But if you want to use that new feature, you have to use, version 2.5 the feature was introduced in, because 2.4 didn't have it. And so when you use that feature, you specify and say, I need 2.5 or greater, right? And so that's what you do in a mod file. Mod file can be more granular, but you can only specify the minimum version.
Yeah. So my problem would be with that is that, say you have a bug fix in 2.5.1, and there's another bug fix in 2.5.2, but it's actually the reverse bug fix. Right, so I only want 2.5.1. I really don't want to have 2.5.2.
Yeah, I understand your situation.
Yeah.
There is a solution to it.
Okay.
So the other part of this is, if you only want 2.5.1, then make that your minimum version. It will never upgrade more than that.
Okay.
Okay.
Yeah.
Unless something else specifies specifically that they want 2.5.2. Of which case, that's the version that's going to happen, but they're the one who brought that bug fix in.
Okay.
Right? And then we need to fix code, right?
So
like when there's bugs, we need to fix code.
So it's sort of the maximum version then? So 2.5.1?
The minimum version algorithm?
Yeah.
Not only, it also only upgrades to the minimum version allowed. Right? Which is a different way of thinking about things. It took me a while to come around.
Yeah.
Once I came around, I realized actually this was brilliant. Because it introduces the lowest amount of change whenever you do an update. It took me a while to get there. But Rust has a lot of papers, too many papers, like many dozens of pages of papers, all about this and on his blog, which we link to on the Go blog. So feel free to read more about it.
Maybe we can do like 2 more questions, just since it's starting to get rather late. So go ahead.
Yeah. So package management is still handled globally, isn't it?
I'm sorry, say it one more time.
So package management is still handled globally. So GoPath and there are proposals like
Good
Vigo,
question.
Vigo, whatever.
So the question is, package management still global?
Yeah.
Is in Go 1.0, we made this directory called GoPath, where all Go code lived. All dependencies lived, all the code you wrote in there. It took me about a year to not hate it. Once I stopped hating it, I actually learned to really like it. Although I've done workshops a lot all over the world, every single new user trips up with it. With our new, in Go 1.11, it's opt-in, right? This dependency management is optional in it. When it ships for real, it eliminates the need for GoPath. So you can, with Go 1.11, you can do this. You can put Go code in any directory. It somewhat isolates your dependencies into your own space for that project.
Okay.
So each of them are independent, and they can exist anywhere on your operating system. As long as there's a Go mod file, it'll work just fine.
Okay.
Which Vigo will create for you. Or in Go 1.11, Go will create for you, the mod file. Okay, I don't know who's next, but there's lots of hands and only one of you can ask.
So.
Okay, hey, all right, in your talk you showed the wonderful power of GoFix, and then at the same time you're talking about how if you add something to the language, then it's forever. These feel contradictory. Like, can you elaborate a little bit why you couldn't just add like any old generics and then go fix them into better generics later?
Does that sound like a good idea to you?
Yeah, it sounds like a good idea.
Okay, there is millions of like when we started, all of it could sit in Russ's editor. Now Go is spanned across many industries and many millions of programmers. The idea of making a breaking change and just say run Go fix, it's going to fix it for you, seems very risky.
Okay, that answer. So that's a limiting principle on GoFix, I guess.
Yeah, GoFix is not a magic wand. Like, it'll fix things for you, but there's always ways to write things that GoFix might, like, people have found very clever ways to do stupid things. And GoFix will not catch all of everything. And so, you know, it's a good tool and it does a lot, but there's things it won't catch. It's always going to require a little bit of manual, particularly if you did things in an obscure way. So, yeah, and when we talk about adding generics, I think that's a world of trouble that we would not want to do. So GoFix works really well, but is not a magic wand. If you do lots of like nested things, it's not going to catch those. It's going to do very straightforward changes.
Okay, so yeah, definitely, but maybe come accost him in person. So I'm going to take this.
Yeah, I guess I can be accosted in person.
Yeah,
after
you should
this
just come
by
running up
anyone.
and ask questions afterwards. So let's thank Steve for